Okay, I would like to thank the organizers for the kind invitation to this very nice program. So my talk will be about quadratic gravity and its phenomenology. Before talking about phenomenology, I will briefly... Oops. Before it works. Okay. Yes. I will give you the definition of quadratic gravity and some motivation for considering it. In quadratic gravity, we have additional terms, apart from the Einstein-Hilbert and cosmological constant terms, which are quadratic in the curvature. Like r squared, which is scalar squared, and the r mu nu term, where r mu nu is the Ricci tensor. And of course, you can add other terms, but you can show that these are combinations of these two plus boundary terms. I will not consider them for this reason. Such terms are unavoidably generated by matter loops, which is, to me, the basic motivation for considering these terms, such as this one, where these dashed lines is scalar and the double wavy lines are external gravitons. Indeed, at one loop, the renormalization group equations for C2 and C2 primes, the corresponding coefficients, are given by these expressions, where NV and F and S are the numbers of vectors, while fermions and real scalars phi A, which also can have no minimal couplings psi AB, which appear in the Lagrangian density L in this way. So you can see that whenever you add matter fields, which are of course necessary for phenomenological reasons, and you get a running of these coefficients, so it's not consistent to take them equal to 0. What happens if you take into account the dynamics of the gravitons? Then with these quadratic terms, gravity becomes renormalizable, as shown by Stelle. And the intuitive reason is that in the UV, the theory is the most general scale invariant one, when you can neglect the cosmological constant and Einstein-Hilbert term. I will also rewrite the pure gravitational Lagrangian in this form with these first three terms. The r squared term with the coefficient that we'll call 1/6 F0 squared. The w squared term, the square of the Weil tensor, w mu nu rho sigma, with the coefficient that we call -1/2 F2 squared. Then I will have the Einstein-Hilbert piece plus a cosmological constant, including this LEH, and then, of course, the matter piece. Another motivation for considering this theory is that the Higgs mass can be naturally much smaller than the Planck mass in this theory. Here I'm using Toft's definition of naturalness. Physical quantity is naturally small when setting it to 0 leads to an enhanced symmetry. And this ensures that quantum corrections respect the smallness of the physical quantity. In this theory, you can actually consistently compute the quantum corrections to the Higgs mass that we call delta MH, because the theory is renormalizable. And you get a correction from gravity, which goes like this, where MPL bar is the reduced Planck scale, and these Fi are the parameters that I've introduced before. So you see that if you require that the gravitational corrections to the Higgs mass squared is not exceeding in order of magnitude the Higgs mass squared, then you get that F2, the coefficient, that there is also corresponding bound for F0, but let's focus on F2. F2 has to be not exceeding in order of magnitude the scale of 10 to the minus 8. This is a pretty small scale, but one can show that the renormalization group equations respects this smallness as a consequence of the fact that there is actually symmetry that we're going to talk about in a few seconds. Quadratic gravity is actually a realization of a more general scenario, potentially more general scenario called Softner gravity. The problem of Einstein gravity from the point of view of consistency, but also from the point of view of naturalness of the Higgs mass, is that Einstein gravitational interactions increase with energy. So they are small at accessible energies, then become larger and larger till they become non-perturbative and out of control at the Planck scale. So the idea is to consider some modified gravity theory, which is softened above a scale that I will call lambda g, in the sense that gravity then becomes smaller, gravitational interactions become smaller and smaller as energy increases, but it mimics the Einstein gravitational behavior at low energies. So in this generalized scenario, the gravitational contribution to the Higgs mass from dimensional analysis given by this correction in order of magnitude where Gn is the Newton constant, lambda g is to the power 4 because of dimensional reasons, and also this 4 pi squared appears because this is a quantum correction that appears first at one loop. So requiring that you have naturalness, you get a bound in order of magnitude for lambda g, which is 10 to the 11 GeV, which is consistent with the previous one given the constant context of quadratic gravity. The reason why this happens is because when this is satisfied, the Higgs field acquires an approximate shift symmetry that protects MH. And this shift symmetry has to be respected also by the matter sector, not only by the gravitational sector. And this gives you bounds on the possible beyond the standard model masses and interactions as well. Another possibility in this theory is to address the strong CP problem. Let me recall you what the strong CP problem is. One can add the P parity and CP, charge conjugation times parity evaluating term, to the QCD Lagrangian, which looks like this, where theta is an angle, as a coefficient, and this GA mu nu is the gluon field strength, and G tilde is the dual, where epsilon mu nu alpha beta is the Levi-Civita tensor. An important point is that theta term has a physical effect only in the presence of quark masses, as when quark masses are zero, then you can redefine the field in a way that this term can be rotated away, but the field redefinition cannot affect physics. An example is the electron-neutron dipole moment, which gets a correction from this term, which goes like this, where E is electron charge, and pi is the pi of mass, and here you have the for a third power of the QCD scale. So you get a very small contribution, but not small enough, because experimentally this quantity is much smaller than what you get here for theta of order 1. And indeed, you get this bound for absolute value of theta. In quadratic gravity, coupled to the standard model and some of its phenomenological completions, in particular extending the standard model with the right-handed neutrinos below the electroweak scale, such small value can be natural because the sources of CP breaking are so small that the quantum corrections to this quantity are much smaller than 10 to the minus 10, shown in the context of the standard model by Alice Gaillard. And I basically extended this result in the presence of quadratic gravity. And this puts bound on the possible phenomenological extension of the standard model. One possibility is to respect this is to add just right-handed neutrinos below the electroweak scale. But also one can worry about this possible gravitational theta term that you can add, and that spoils P symmetry, because the reason why this works is because P and CP are approximate symmetries in the context of the standard model, are softly broken. So the contribution to theta angle is small enough, but one can worry about this possible gravitational theta term, but this can be removed with the U1 chiral transformation of the right-handed neutrino fields without affecting neutrino energy phenomenology. So one can exploit the presence of these right-handed neutrinos to make this work in the context of quadratic gravity. Okay, all this motivation and plus of the theory come with a price, which is the fact that the Ostrogradsky theorem that states that Lagrangians that depend on the second derivatives have classical Hamiltonians unbounded from below does apply to this quadratic gravity. Indeed, looking at the degrees of freedom, expanding around the flat space-time, for example, one gets a massless graviton, an ordinary scalar, omega, with square mass given by this relation here, which corresponds to the R squared term, and then a massive spin-2 field with some abnormal sign kinetic term, namely a ghost, and squared mass given by this relation, which is the manifestation of the Ostrogradsky theorem and corresponds to the W squared term. So it is removed when you send F2 to infinity, when the mass goes to infinity. Another way to see this by linearizing the theory and computing the Hamiltonian of the spin-2 sector, then one gets an ordinary Hamiltonian, which has, for the massless graviton, which has two helicity states. Here, capital Q and capital P are the canonical coordinates, and this Q is the 3 momentum. For the ghost, which is massive, so you have 5 helicity states, you get a minus sign. Here, Q tilde and P tilde are the canonical coordinates, a conjugate momenta for the ghost. So here you get the manifestation of the Ostrogradsky theorem already at the linearized level in the equations of motion. So one has to address this problem. Let me start by proceeding perturbatively. This means that I will split the metric G mu nu, which is in general an operator, in the classical part plus a quantum fluctuation H hat, where G classical satisfies the classical equations of motion of the theory, and this H hat is a quantum fluctuation. So how can we avoid this, if it's possible, the possible Ostrogradsky instabilities that are suggested by Ostrogradsky's theorem? Recall first that in the free field limit, you don't have a pathology because this minus sign cancel in the equations of motion. Now, interactions. Effective theory arguments tells us that at energies below M2, we should not find runaways, even if the abnormal graviton has an order 1 coupling. Okay, in the limit in which you consider energies much below the gauss mass is, corresponds to the limit in which the mass goes to infinity. At the intermediate case, where F2 is between 0 and 1, we must have intermediate energy thresholds. When F2 goes to 0, you must have an energy threshold over which these instabilities are triggered that go to infinity. And when you send F2 to another 1 value, you get this M2 energy threshold. So in the weak coupling case, F2 much smaller than 1, which is the one that is relevant for the Higgs naturalness, we must have an energy threshold much larger than M2. So we could see the effect of this abnormal graviton without runaways. Yes?
How does this avoid the instability of the vacuum issue?
This is the quantum physics. I will get to the quantum physics later on. This is just classical. This is just the classical theory. And then in the next slides, I will address the quantum issues. So you're referring to vacuum, so it's a quantum state. Okay, this can be made precise in the context of quadratic gravity. And the whole cosmology can only involve energies below this threshold and avoid runaways, as proposed in 2019, and also was numerically checked here and in a number of papers later on. One can derive this threshold more explicitly by some field redefinitions. I will skip this derivation, but if somebody is interested, we can talk about this in the question and answer session, and just go to the final answer for the energy thresholds. What happens for the spin-2 sector is that for energies E much smaller than this threshold, E2, which is defined by M2 over the square root of F2, which can be rewritten like this, the Ostrogradsky instabilities are avoided. And this bound has to be applied, of course, to the boundary conditions, because then the values outside the boundary conditions are dynamically determined by the equations of motion. And analogously, one can show that the Ostrogradsky instabilities are avoided if in the matter sector, the energy, again, thought of as energies for the boundary conditions, are much smaller than a threshold that is the square root, the fourth root of F2 times the reduced Planck scale. So what are the order of magnitude of this? For F2, of order 10 to the minus 8, which is the maximum one compatible with Higgs naturalness, then E2 is 10 to the minus 4, reduced Planck scale, and EM is 10 to the minus 2 times the same scale. So it is clear that it is only during inflation and case the preceding epoch that you can access such high energy scales. Note also that the ghost is completely inactive in an FLRW metric, because this metric is conformally flat. So the W tensor, the Weil tensor vanishes, and so the W squared term doesn't play any role. So only perturbations that break homogeneity and isotropy may destabilize the universe. And there is a nice relation with the chaotic inflation theory by Linde that proposed that we live in one of those patches where the energy scales of inhomogeneities, EI, and anisotropies, that I call EA, were small enough. How small? Small enough to use the homogeneous and anisotropic solutions to describe the classical part of inflation. So one get these bounds for EI and EA, where H is the Hubble rate and U is the potential for the inflaton phi. What happens is that chaotic theory automatically ensures that the conditions to avoid runaway solutions are satisfied, in the sense that when this is satisfied, also the threshold, the bounds to avoid the runaways are satisfied. And I checked this for Starobinsky inflation, Higgs inflation, natural inflation, and other models. On the other hand, the further runaways above the energy thresholds give an entropic rationale for a homogeneous and isotropic universe, also checked in these very famous models and probably holds in many other inflationary models. So this gives you a rationale for why the universe is, the initial conditions for the universe were so homogeneous and isotropic, because otherwise you would get these fatal runaways. Now the quantum corrections. So in the perturbative, so in this theory, basically was thought that initially the universe were composed by several patches where the inflaton and the metric acquires a random initial conditions. So there were patches where the fields were very inhomogeneous and anisotropic, and just accidentally somewhere there were patches where there were enough homogeneous isotropic, and we happen to live in those yeah, and then we happen to live in those patches that are enough homogeneous and isotropic so that inflation could take place and life could emerge. Okay. A first interesting point that I've already mentioned is renormalizability of this theory. Renormalizability implies that the quantum Hamiltonian governing H hat is bounded from below, as shown by Stille. So the vacuum is stable because the vacuum is the state with the minimal energy. This was your question. Because the Hamiltonian is bounded from below. However, the price to pay is that the space of state of states must be endowed with an indefinite metric for this to hold. So the question is, how can we define probabilities consistently? Because, sorry? Ah, okay, yeah. A pair of gravitons. Yeah, this phantoms? You mean ghosts? Ghost. Yeah, this does not happen because the vacuum is the state with the minimal energy. So energy is conserved. The ghost has positive energy because it has an energy that is above the vacuum energy. The vacuum is the one with the minimal energy, so it cannot decay into ghost plus gravitons because then you will get energy equal to some value equal to energy equal to the bigger value, but energy is conserved. So this is not possible. Okay. Yep. In this case, I'm referring to the flat space. Yeah. I will come to the non-perturbative definition of this theory later on. So this is a perturbative approach that is basically referring at the quantum level to the flat space quantization, and also to quantization. It was actually performed in another case, a quantization around the FLRW metric. And basically, there's nothing else in the literature so far. And then later on, I will give a non-perturbative background independent definition of the theory. So this is the perturbative part. Okay. Okay, so to define probabilities consistently, I will first define what an observable is. Here, you don't yet have an inner product, because if you use the indefinite inner product, you get in the Born rule, you get negative probabilities. You can try to define negative probabilities, but just assume that makes no sense, negative probabilities. So, because I didn't find a meaning to negative probabilities, so just assume that standard definition of probabilities are positive or zero, and then sum up to one. So you don't yet know what the inner product has to be in order to apply the Born rule, or maybe you have to modify the Born rule. So let's not assume an inner product. So you have to define the observables in a different way, not just Hermitian operators, because this refers to the inner product. So I will define an observable as an operator with a complete set of eigenstates. In the sense that any state psi can be decomposed in a combination with some a priori generic set of complex coefficients Ca times A, this set of eigenstates. And for example, one can show that the basic canonical operators Q and P, or capital Q, capital P, if you want to use the previous definition, have a complete set of eigenstates. Next, interpret A as the state where capital A, the observable, assumes certainly the value A, or corresponding to label A, that I will call deterministic Born rule. And next, to find what the probabilities are in the generic state psi, we can reason as experimentalists do. We prepare mentally a large number of times, we call n, large number n of times the same state. So we consider a big state, capital psi n, which is the direct product n times of the state psi times some overall coefficient nu to the n, where nu is given by this expression. And then we can decompose this in the basis A1, AN. Next, we define a frequency operator, Fa, which counts the number and A of times there is the value A in the state A1, AN. which means that Fa applied to this direct product A1AN gives you the number of times an A in the state A1AN divided by N times A1AN. Just a definition. The important result is that one can show that in the limit where n goes to infinity, so you repeat the experiments in principle, an infinite number of times, a large number of times, physics, Fa times psi n is equal to Ba times psi n, where Ba is the Born rule. Okay. So what happens is this psi n tends in the limit in which n goes to infinity to an eigenstate of the frequency operator with eigenvalue Ba, which gives you motivation for the Born rule. In this sense, all coefficients in the basis A1, An converge to the same quantities. So the probabilities, you can see, are positive and sum up to 1 at any time. In this sense, in this generalized sense, the theory is unitary. If you sum over A here, you get 1. And now you can reconstruct what the inner product should be. The real inner product should be in the Born rule. We can define a norm operator, PA, by this relation, where for any pair of states, psi1, psi2, we denote the indefinite metric with psi2 times psi1. So we insert in the indefinite metric this operator that by definition gives you this Kronecker delta. And this definition above provides a positive definite inner product, psi2, psi1a, which is by definition this quantity, is a positive definite when psi1 is equal to psi2. In general, it's complex, like in ordinary quantum mechanics. So we recover the full probabilistic Born rule. Here you can see, because A is normalized to 1 by construction, but expressed in terms of the positive norm, not in terms of the indefinite one. Another unusual feature at the quantum mechanical level of this quantization is what we call the Dirac-Pauli quantization of canonical variables, introduced by Pauli, that elaborated on a previous work by Dirac, and we applied this method to full derivative theory in 2015. A note is normal with respect to the A norm. This norm that is constructed by inserting the PA operator, the norm operator PA. So we can split A into the sum of Hermitian AH and anti-Hermitian AA operator with respect to the A norm, that they commute with each other. So we can restrict to operators that have purely real, lambda A is real, or purely imaginary, lambda A is purely imaginary eigenvalues. The first possibility for canonical coordinates is the standard one that you have in textbooks. The second possibility is what we refer to as Dirac-Pauli quantization. In quadratic gravity, there are also observables that realize the second possibility, because this is the only way Hamiltonian of this form have a spectrum bounded from below and normalizable eigenvalues, eigenfunctions. Now we go to non-perturbative definition and background independent formulation of quadratic gravity, because everything we did so far is perturbative. The key idea is the construction of a consistent Euclidean path integral, PI. To obtain this, we need first the quantum Hamiltonian. To construct this, let's first assume Gauss coordinates, where the metric can be expressed in terms of a three-dimensional metric Gij. This is usually time. And in Ostrogradsky's canonical method, one can choose Gij, this three-dimensional metric, and the time derivative, the derivative with respect to t, g delta ej, as canonical coordinates. Here I'm also putting conventional -1/2 factor. And the following fields as corresponding conjugate momenta. Pi aj defined like this, and Pij defined like this. The classical Hamiltonian density is then given in terms of the classical Lagrangian density L by this expression. And H depends on pi j, unlike L. One can show that L does not depend on pi j, which means that the dependence of H on pi j is only given by this quantity here. And this, if you use standard quantization, leads to a divergent path integral. The Euclidean path integral is not convergent if you use standard quantization. So the idea is to use the Dirac-Pauli quantization for Kij such that this term becomes purely imaginary and its oscillation is not problematic for the conventions of the Euclidean path integral. And with appropriate ordering, one obtains that the transition amplitude between a state at Euclidean time tau I with coordinates qi, canonical coordinates qi, to a state with canonical coordinates qf at Euclidean time tau f, in the presence of an external source Gij, is given by this path integral expression, the sum over all possible three-dimensional metrics, delta G, of the usual e to the minus s e over h bar terms, plus this interaction with the external source, with fixed boundary conditions. SE is the Euclidean action for quadratic gravity, so it can be written in these terms. So alpha, beta, gamma, and lambda are bare parameters, and C is a coefficient that has to be thought of as part of the metric, which is the product over all Euclidean space-time points of this quantity here, where delta V3 is the three-dimensional volume element, delta tau is the Euclidean time element, and G is the determinant of the metric. This was done in Gauss coordinates, but one can construct the path integral formulation for transition amplitudes also in a generic coordinate system, and one gets a formula which is reminiscent of the Fadev-Popov quantization. You get some determinant of f, where f is some gauge fixing function, delta f divided by delta xi, where xi are the four-dimensional diffeomorphisms. This dg is the four-dimensional metric measure, which is c times the previous delta g times delta xi, even here. And the convergence of the Euclidean path integral requires the following conditions on the bare quantities in a generic gauge, which are also sufficient conditions in, of course, in a space-time discretization. And the interesting fact is this is opposed to the case of Einstein gravity, where there are no values at all of the parameters for which the Euclidean path integral could converge, as the Euclidean action is always unbounded from below. It's a so-called conformal factor problem. Another point to keep in mind is these parameters are bare parameters. They generically diverge as a function of the cutoff to ensure the convergence of the physical quantities. So it is not possible to infer that the same conditions hold for normalized quantities. In particular, you cannot conclude that the physical cosmological constant is always positive from this. One can also construct a path integral for Green's functions. For the Euclidean signature, the generating functional of Euclidean Green's function z of j is given by this expression here, where this prefactor means that you have, as usual, to divide this quantity by the same quantity with j equal to 0. And in the Lorentzian signature, you get a similar expression. This is quite formal, as usual. This quantity has to be thought of as the analytic continuation of the Green's function generated by this functional to the imaginary time. And with this generating functional, one can reproduce previous perturbative calculations performed expanding around the Minkowski metric, such as those performed by Stelle in 1977. One can also, with this formula, construct the effective action of quadratic gravity. One starts from the expectation value of G mu nu in the presence of an external source, which by using the previous expression can be computed with this path integral formula. And the quadratic gravity effective action gamma can be defined as a functional of G mu nu j in this way, where W is defined as by this expression here, and this subtraction is a standard subtraction in quantum field theory. With this effective action, one can take the classical limit, h bar going to 0. And this limit, the path integral, is dominated by a metric satisfying this relation here. And we can call the solution to this equation Gj, because it depends on j. And one can show that when h bar goes to 0, then gamma can be expressed by this quantity here, where Sran Gj is the starting action, classical action, with renormalized coefficients, which is why I write Ran here, and computed in the corresponding Gj, namely the solution of this equation here. So here the renormalized quantity appears, not the bare ones. So the classical limit is described by the starting classical action with renormalized coefficients. And the reason why this can happen, even if the spectrum of the quantum Hamiltonian is bounded from below, is because of the presence of the Dirac-Pauli variables, which allow to break the equality between this functional of the canonical coordinate q, coordinates q and corresponding momentum p in the classical limit, and the classical Hamiltonian that I call here hc, which are the same in standard theories without the Dirac-Pauli variables. And this is the reason why this can happen even if the quantum Hamiltonian is bounded from below. Nevertheless, the metric remains real because the expectation values of canonical variables are always real. Doesn't matter if they are standard or Dirac-Pauli variables. With this non-perturbative definition, one can do some quantum cosmology. In quantum cosmology, one describes the universe through a quantum mechanical wave function, as proposed by Hartle and Hawking. But this proposal was based on Einstein's gravity with the conformal factor problem, as I mentioned before. But quadratic gravity in the quantization specified does not suffer from this problem, so one can rigorously implement the HH idea here. So an interesting result is that in our fully quantum construction, the configuration that leads to the smallest action corresponds to peaks in the wave function of the ground state and then homogeneous and isotropic. This can be shown by using the path integral expressions I showed you before, while in homogeneities and anisotropies lead to a larger action and are associated with excited states. So there is an interesting relation with the finite action principle proposed by Lennartz and Stelle in a couple of papers at the classical level, but this uplifts this proposal to the full quantum level. And also the homogeneity and isotropy of the initial conditions for inflation are explained rather than postulated by some quantum generalization of the explanation I showed you before in the classical case. It is only in the nearly homogeneous and isotropic patches that inflation can occur and observation can eventually made. So this is a picture of the primordial universe, and you can live only in those patches that are initially enough homogeneous and isotropic for life to emerge. So since we talk about inflation, let's see what inflationary observation. So the explanation.
So this great inflation takes place. This is not an explanation. This is an initial condition for inflation. This does not show that this is not a resolution. It's just required.
Yeah, so this is true. This is not true in general, but in this theory. No. I mean, what I'm stating is not true in general. Yeah. Yeah.
But the deflation can occur. This means that is a requirement for the onset of deflation. It's not an explanation.
So the explanation takes place because if you assume that initially the patch was not enough homogeneous and isotropic, then in those patches these fatal runaways of Ostrogradsky theory took place that are.
We have shown that ages ago. So I know that very well. But what I'm saying, I don't understand that this is an explanation.
Because you cannot live in those patches, because in those.
It's not more profound than that. It's a limitation for the validity of the proposal.
No, but in those patches, it's not that the model does not work. It's that you have Ostrogradsky instabilities localized in those patches.
Given that you have this ghost, you have this kind of pathology of the theory, that means that it will not work. It's not. I don't get that as an explanation. I get it as a requirement for the validity of the proposal.
Yes. No, but how you get inflation is. So this is not a specific model, but is a class of models of inflation. So then inflation, you can have different. So you need to have at least one scalar. So there is for sure one scalar here, which is a scalaron. You can have scalar inflation, also known as Starobinsky inflation, but you can also have inflation triggered by other fields, such as the Higgs field or some natural inflationary theory. So depending on what matter fields you put in, you can have different inflationary models. So, yeah.
She was saying that you start from a universe which is not homogeneous in the isotropic, so you have instabilities, and then you will have.
No, but this is not just one universe. Initial condition that you're assuming. So you have this chaotic inflationary condition where you have patches that are.
That ugly stable universe, you don't know how it would be.
Ugly, stable, or unstable. Yeah, but so this.
What is the? It cannot is like anthropic. It's not far saying that. Okay, otherwise we will not have a universe, so the universe must be isotropic.
It's not a condition. It's not a condition for the universe. It's not. It's a condition for the patch where you can live. So.
Maybe at the end of the day that that's the end of quantum gravity, and that's how it looks like. I don't think so. Nevertheless, what I'm saying is that this is not an explanation. The fact that you need that doesn't mean that it's the same thing that people go around and say because we have a, I don't know how many vacuum string theory that means that we solve those calculations. No, it's a pathology which exists there. So I don't get it.
So is that because the initial state of the universe has to be thought as chaotic inflationary initial conditions. So you have for different regions of the universe.
It's not that the universe has to be like that.
Well, this is the most general initial condition. Well, well.
I mean, but independent of the initial condition, I think his argument is related to the papers by Lars and Stelle, and the idea is you have the path integral, okay? And if assuming there is an assumption, if your fundamental theory is a quantum field theory whose main action is quadratic gravity, forget for a second about instability, so forget about that. Then inhomogeneous and anisotropic configuration are suppressed, which does not happen with plain Einstein vector. Then there are additional problems.
You said it by yourself. If I take, if not.
No, well, it's not. It's not. It's not. So there is some relation. There's some more. There's some more to this. Yeah. Yeah, I understand. Yeah. Exactly.
Yeah, there is an assumption, and we can discuss.
Well, this, to me, there's no assumptions. You're just assuming all possible initial conditions around the universe. So, because if you don't live in those, so you cannot live in those regions of initial universe which are not enough homogeneous and isotropic, because they essentially collapse with respect to the other regions which are.
Scientific explanation. It's just
well,
you will have something else, something.
I might take another model of inflation.
What? It's an explanation to me.
Because there are probably 15 minutes left for.
Yeah. 15 minutes. Well,
15 minutes.
I was assuming to stop the time when I received a question. So,
so you can
okay. 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 50 minutes up to the end of my talk, without question. Including a question.
Some questions.
Okay. Okay. Let's see if I manage. Okay. So let's go to the inflationary observables then. For M2 larger than the Hubble rate h, there are no differences compared to the general relativity. So in the limit which mass goes to infinity, there are no differences. But for M2 smaller than h, there are two basic differences. One is the tensor to scalar ratio R gets suppressed with respect to the Einstein-Hilbert value Re, as shown here. So h during inflation. Yeah. So so models that are excluded for a large Re, such as quadratic inflation, become viable. The second point is that there is an isocurvature mode, which fulfills, however, can fulfill the observational bounds depending on the model, corresponding to the scalar component of the abnormal graviton. Here you have the power spectrum of this mode, which is essentially 1/5 of the tensor perturbation. The correlation power spectrum with this curvature perturbation is highly suppressed. And here I show that basically this can be within the bounds of Planck, even for models that are predict a value of Re that is excluded by Planck. So basically, there's a bound on Re which is weaker than the one on the tensor to scalar ratio in Einstein gravity. So more models are viable in this construction. As I mentioned before, you can have scalar inflation or natural inflation, which is inflation triggered by pseudo-Goldstone boson. And in this case, one can elegantly obtain a UV completion within some asymptotically free QCD-like theory. And the potential density will be written this expression where lambda is some energy scale and F is another energy scale. And you can have other possibilities. But let's focus on these first two, which are quite well motivated. The conditions to avoid the Ostrogradsky instabilities are satisfied in all these cases, as I mentioned before. And for natural scalar inflation in quadratic gravity, one can go to the pure natural inflation or to the pure scalar inflation by taking respectively a small and a large value of this parameter here. Here I give how the inflationary Hubble scale and energy scale lambda depend on rho. And here I give the same quantity by fixing rho and varying f, rather than fixing f and varying rho. But the interesting plots are this. For M2 much larger than H, so Einstein-Hilbert limit, you get this prediction for an S, the spectral index, and the tensor to scalar ratio R as a function of rho for a fixed value of F. And here as a function of F for a fixed value of rho. So you get some bound to get inside the 1 sigma region. If you take instead M2 below the Hubble inflationary Hubble scale, then you get a suppression, the tensor to scalar ratio, and you get inside the 1 sigma region, even if rho is quite small. Here is by varying rho and fixing f, and this is by varying f and fixing rho. So more models are viable. What about now the cosmological constant? We mentioned the hierarchy problem and the strong CP problem. So what about the cosmological constant problem? I will focus on this proposal that can be applied to several gravitational theories, that is unimodular gravity, where one requires by definition that the space-time volume is not dynamical. And one can show, as Roberto Percacci did, that in the classical limit, the theories, the gravitational theory with this unimodular condition or without the unimodular condition are exactly the same. The cosmological constant is an integration constant of the classical field equations in unimodular gravity. This is the only difference at the classical level. So for this reason, the CC and the vacuum energy are independent, and unimodular gravity addresses the old cosmological constant problem, which is the problem of explaining why such constant is not at least as large as the largest particle mass scale, because this mass scale contributes to the vacuum in standard gravity, but does not contribute to the vacuum at all in this unimodular gravity. So there's no reason why this should be of this order of magnitude. So this is an interesting theory then. So can we distinguish unimodular and non-unimodular theories at least quantum mechanically? In this quadratic gravity, one can use the non-perturbative and background independent quantum formulation of quadratic gravity with the path integral I showed you before. And one can insert the following constraining delta function factor in the Euclidean path integral, which implements this definition of the unimodular gravity. While in the Lorentzian path integral, we insert this, where G now is the determinant of the Lorentzian metric. Delta T is instead the real-time element, and the product is over the Lorentzian space-time points, and delta V is the Lorentzian volume, four-dimensional volume element, and this delta VE is the Euclidean four-dimensional volume element. One can express this in terms of an auxiliary field L, and recover the auxiliary field formulation of unimodular gravity. Then how can we distinguish the quantum theory from the quantum level, the unimodular theory to the non-unimodular theory? First, note that this formulation does not break general covariance. And so then we can take a standard FLRW metric at the classical level, where A is the scale factor and U is the conformal time. And also we can choose the conformal Newton gauge, since this does not break general covariance, and write at the quantum level the metric as this plus quantum operators that parameterize the scalar perturbations psi and phi, the vector perturbations vi, and the tensor perturbations hij, which are constrained by these conditions in this gauge. Next, notice that the determinant of a metric is reduced to a C-number function in modular gravity, so be fixed to some fixed non-dynamical C-number value. So at the linear level in the perturbations, you get this condition here, because G can be expressed in terms of the scalar operators only. And then assuming that inflation is driven by a minimally coupled scalar field, I haven't done the proof, I haven't found the proof yet for a non-minimally coupled inflaton. One finds that psi goes to 0 in the superhorizon limit when U goes to 0 and A goes to infinity. In this limit, the curvature perturbation R acquires the expression in Einstein gravity. The predictions for R and S are the same as in quadratic gravity without the modular constraint. However, there is a curvature mode B present in quadratic gravity decouples in unimodular gravity. But since this can be tested by future CMB experiments, you get a way to distinguish between unimodular and unimodular quadratic gravity. This formulation does not address the new cosmological constant problem, which is explaining why the cosmological constant has the observed value, which is a different problem. It's not the old cosmological constant problem. One can address this anthropically. We can consider the post-inflationary cosmology and assume that the inflaton energy density is transferred as radiation to the observable sector, which includes the standard model fields at low energy. And this can be done, for example, in Scaron, natural, and Higgs inflation. And life is clearly impossible in both inflationary epoch, because the Weinberg's bound is not satisfied, and in radiation epoch says the universe is too hot. As time passes, the radiation energy density decreases and the temperature drops, so that the matter-dominated universe emerges at some epoch. But since the matter density also decreases with time, eventually the energy density due to the cosmological constant that I call rho lambda surpasses again rho m. But in order not to violate the entropic bound, again, the same bound by Weinberg, rho lambda should not be much larger than rho m. And life takes time to develop, so it is reasonable to find a scientific community able to measure the cosmological constant at the latest possible epoch compatible with this bound, which is when we live. So this is a sort of landscape, but it's a landscape in time, not in different configurations, space configurations of different field configurations. A type of landscape that was also discussed by Banks in 1985. One can, I guess, my time is is more or less over. So many questions. So just a brief discussion about decay and scattering. So basically, if one applies this theory to decay and scattering, one gets modified formula. And an interesting thing is that if you go above the Planck scale, then lots of gravitons and ghosts are radiated. So the theory basically doesn't want to go over the Planck scale, because if you go over the Planck scale, this loses energies emitting with these gravitons and ghosts because of an infrared divergence. So basically, you cannot physically take the infinite energy limit. And then there is a nice prediction for ultracompact objects at scales below the scale lambda G defined before. Basically, when you go below this scale, ultracompact objects do not have horizons. Microscopic ultracompact objects do not have horizons. And this is the proof. It can be applied in specific cases too, because this is a generic proof. And you can have these ultracompact objects also satisfying the bounds given by the argument before to avoid the Ostrogradsky instabilities. And this is a summary of all findings. I will leave you with this slide, since fortunately I don't have time anymore, but we can discuss later. Thank you very much.
Thanks, Alberto. We have time for the one or two quick questions, Robert.
36.
Sorry?
I think it was slide 36.
36.
Slide 36.
36. Okay.
I was confused.
Yes.
If you have phi equals 3 psi, psi goes to 0,
Mhm.
that means phi goes to 0 as well. So is that in contradiction with observations?
So
Doesn't
this
that
is
mean that we have no-
so this holds only for, as I stated before, only where you have energies, Hubble rates above the Gauss mass. So this Gauss mass is very high. So this holds only at inflationary scales. When Hubble rate goes below M2, and these conditions do not hold anymore, because the theory is essentially Einstein gravity. Then you don't have this extra dynamical degree of freedom, at least in the non-unimodular version. So you get all the predictions of Einstein gravity at large distances when h goes below M2. M2 is 10 to the not below 10 to the 10 GeV. So the one inflationary scale is below, those conditions do not. You just get
Okay, so this
you
is
just
the
get GR.
ultraviolet-
Sorry,
It's the ultraviolet limit.
is the ultraviolet limit? Yeah.
There is another question by Guy.
Face value. So I don't work with these kind of theories, but at face value, everything looks quite impressive, and you are like tackling many different problems. Of course, there are many communities that are not taking those theories, I guess, and working on that. But since you work a lot on that, I wonder, from your point of view, what is maybe problematic or something that actually doesn't work super well that might be preventing people from adopting those models?
So the point is that so I made a construction that for which so far I don't find a no-go problem. Let's say, and this so I don't claim I found a proof that no-go theorem can be found. So it's possible that maybe in a month, by making more computations, I will find that this theory maybe predicts something that is not observed on the. Or there is well, mathematical inconsistency. I wouldn't say. Maybe the problem is to define the continuum limit of the theory, because I didn't address this. So it's not proof, for example, that the continuum limit exists. So it is proved that in a fixed space-time discretization, the path integral is consistent, well defined in a region of parameter space, unlike the Einstein gravity. But it is not proved, as it's not proved also actually in QCD, that if you take actually the continuum limit, this converges to some finite value by choosing the bare parameters appropriately. So there are some connections with this dynamical triangular quantization. Yes. That is done. So the difference is that that is done for a Lorentzian metric, while here I find it important to start from the Euclidean path integral, because there's no consistently mathematical definition of quantum field theory in the Lorentzian signature directly. The Lorentzian signature of quantum field theory has to be defined in standard quantum field theories as an analytical continuation of the Euclidean theory. So I don't see how to demand that even including gravity, it's possible to stick from the very beginning to Lorentzian signature. Yes.
People maybe don't work. Some people don't work on this because they are afraid of ghosts.
Yes.
I would ask, why do people not? Some people don't work on this theory. I would say because they are afraid of ghosts. That's why.
Yeah, I thought that the question was somehow different, you know.
No, just because why people don't want, why not so many people?
Yeah, of course, yes, yeah.
That's the reason.
So if you want to stick to quantum field theory approach to gravity, which is computable so far. So far, I don't find any other option. So there is asymptotic safety, I know, but you know, you have problems with computations. You can try to address the problems there, or use another approach that is this one that has also some open questions.
Robert, is that a quick comment or okay?
It's a question which we have no answer, but it's a question for you to work on. So if you work with the Euclidean path integral, you have Euclidean Green's functions, you have to show reflection positivity. If you can't show reflection positivity, you don't have a Minkowski signature theorem. So that's for you to think about.
So you mean you mean unitarity? You mean that this is related to?
It's about the Schwaber accident.
So no. So this is yeah. This is also an open question if you want to define rigorously the theory. So at some point you have to define the analytic continuation of the generative functional for Euclidean path integral to the Lorentzian signature, and
that you have reflection positivity. Otherwise you cannot do it.
And we can postpone this discussion to the open discussion session. So yeah, so let's thank Alberto again. And